Continuing in this series of videos, I don't know what we're doing exactly. Learning physics and basically trying to understand their model and compare it to other interpretations of the facts. I suppose I would add that you often see experiments done, and they're just kind of done one way, and not much is varied or changed in the experiment to sort of kind of tease out of the event what exactly is happening. And that's I'd say a flaw in how physics is approached and taught. Just my opinion. So on magnetic fields, Lorentz force, torques. So some of this is starting to get to these distinctions between their jargon. They have this EMF, electromotive force, and then they have the electric field, and then they have this Lorentz force, and then they have magnetism. And I'm arguing it's all the same thing. It's just in different places. So you're just you have this electron energy and the proton energy, and the electron energy is the significant factor here, and the fact that these electrons reflect this energy. So if you have two electrons in proximity, the energy will reflect back and forth. And if you have a row of electrons, theoretically you can push one electron and it pushes all the electrons, every single one of them. And the force becomes sort of permanent, like a usual reflection just reflects off something and disappears into the environment, space or whatever. But in these closed quarters, the energy, the photons, bounce off more than one thing. Kind of like the ones in this room are sort of inevitably going to be converted into radiation I can't see, infrared. But they'll bounce around a few times before that conversion happens. The light off of one thing will bounce off another thing and another thing, and the photon. But it's inevitably going to be absorbed, and in that absorption process likely converted from a higher energy to a lower energy, and eventually becomes invisible. So kind of interesting. But this is happening in different levels for these electrons. So in certain circumstances the force is like a laser beam. It's right between the electrons, and in other circumstances it's going this way and that way, and in other circumstances it's just going in one way. And these are all the things that make the different manifestations of the force have different impacts. Difference between cannonball and bullets. Both effective in a war, but effective against different things. One stops, battleships, and one stops midgets in motorboats.
So far, we have only discussed in this course electricity. Calm down. But this course is about electricity and magnetism. Today, we're going to talk about magnetism. In the 5th century BC, the Greeks already knew that there are some rocks that attract bits of iron. And they are very plentiful in the district of Magnesia, and so that's where the name magnet and magnetism comes from. The rock
It is one of those things called a coincidence, an ironic coincidence kind of a thing, a strange, bizarre kind of thing, that magnesia, and the word magnetism, and it has that mag in it, like magnification, and it's just kind of funny that in fact, a magnet it magnifies this force in a sense by directing it and filtering it. It's a purification. So I guess it could have been purificatia that they found it or something, but it's just kind of funny that its name is completely unrelated to that magnification kind of connotation, and it fits so well.
Rocks contain iron oxide, which we will call a magnetite. In 1100 AD, the Chinese used these needles of magnetite to make compasses And in the 13th century, it was discovered that magnetites have two places of maximum attraction, which we call poles. So if you take one piece of magnetite, it always has two poles. Let's call one pole A and the other B. A and A repel each other, B and B repel each other, but A and B attract each other.
Right, very simple, and that's essentially the whole system is based on that premise. The electron and the proton are the correlates to the north and south poles, and the force itself has a correlate of electron force and proton force. And that's what makes all of the rest of it happen.
There is a huge difference between electricity and magnetism.
There really isn't. And again, I can say it in different ways, but it's like the charge phenomenon, right? You can put charge on one surface. So the charge, the effect, is only happening in one direction, not in both directions. So you can see if you're coming at the object, you're not feeling any charge. There's no force change on one side, and as soon as you get to the other side, you're getting pushed. So you could sort of see you could be coming down into a charged plate, and you're, say it's negatively charged and you're negatively charged. You're not feeling anything, and all of a sudden, poof, and you're getting pushed. A magnet can't do that, because it's radiating in all directions. So charge can do something a magnet can't do. And a magnet, you can think of it as like the pressure is low pressure. It's low voltage but high density, you could almost argue. So and charge is high pressure and low density. It's just a surface phenomenon. So the magnet is creating a thing throughout its entire structure, its entire mass, and the charge is just something on the surface of any heavy thing, or it doesn't matter, mass doesn't matter, just matters surface. And so it's very thin, where this is a dense thing. And that's also having an effect. So it's high pressure on a thin surface versus low pressure but high density. These are ways of understanding distinctions, that it's really the same thing, just subtly different manifestations of the same thing. They're both filters. They're just filtering differently, subtly differently.
With electricity, you also have two polarities, but you are free to choose a plus or a minus pole. With magnetism, you don't have that choice. The poles always come in pairs.
They always come in pairs in the sense of the way you're defining a magnet. So again, the electron and the proton are the monopoles of magnetism. Without them, you can't make a magnet. So why this distinction? Yes, when you make a single pole, it'll behave different than when you attach a bipole to it, because now you're polluting your filter. You're putting two opposite filters, attaching them to each other. Obviously, that's going to have that's going to certainly change the field you're creating. So it's kind of an obvious change. And the more you can separate them, the more they become different. But again, it's the same. They're filtering. They're just filtering red, filtering black. Obviously different, but the same mechanism.
Isolated magnetic poles do not exist, or as a physicist would say, magnetic monopoles do not exist as far
as we know. I'm just saying it's so deducible from the facts you already have. You don't have a magnet without the atomics doing the exact thing you're talking about. The atomics are separating. They're creating a dipole. Well, I mean, obviously, if the proton and the electron are creating the thing called a magnet, why wouldn't you recognize that they're the monopoles of magnetism? Without them, you can't create a magnet. The atomic the atomic dipole is the origin of magnetism. So why wouldn't you concede that the electron and the proton are the monopoles of magnetism? It's plainly in your face saying, that's the right answer. Monopoles are easy to find.
As we know, if anyone finds a magnetic monopole and don't think that people are not looking, that would certainly be worth a Nobel Prize. In principle.
Okay, so you heard it. Right? So all these people that are critiquing my claim, I'm just saying that clearly, yes, this seems, if you can unify physics, you should get a Nobel Prize. If you find the monopoles, you should be able to get a Nobel Prize. Yes, these are all things that have been looked for 100 years, and I'm saying, well, look, there it is. I'm just saying, if I'm right, and that's true, that it's just as obvious as I'm pointing out. I mean, the proton, the electron, make magnetism by just moving away from each other. That's a magnet. These have to be the monopoles of magnetism. There's no way around it. There, Nobel Prize, thank you.
They could exist, but as far as we know, they don't exist. They've never been seen.
So again, it's just, so this is the thing where physics is saying these emphatic things that we can't do this, and it's all based on their model. Their model says that these are two different fields, and they're just not recognizing that there's a fundamental, like I say, if you don't polarize the field energy, you can't see anything because you're not recognizing where the energy comes from in the first place, which is the outside, the universe. It's not coming from inside of things. The energy is coming from the outside and be interpreted by the material to create its. It wouldn't have like I said, you can't condense it. You can't make atoms. You can't make solids. You can't make things without that external pressure. And they've just totally ignored the evidence indicating it's a push universe, not a I created it from inside universe. This wasn't an inside-out universe. This is an outside-in universe. And they got that one wrong. And once you get that wrong, you're looking upside down the whole time. You're reading the paper upside down. You're just making the job so much harder.
Electric monopoles do exist. If you have a plus charge, that's an electric monopole. You have a minus charge, electric charge, that is an electric monopole.
Right. You have an electron. That's a magnetic monopole. You have a proton, that's a magnetic monopole.
If you have a plus and a minus of equal strength, that is an electric dipole. Whenever you have a magnet, you always have a magnetic dipole. There is no such thing as a magnetic monopole.
So again, it just happens to be that the atoms are very small, and but the truth is, he's demonstrated you can make a electrical, that is, you can take two charged objects and you can make them into a dipole, and they function like a magnet once you do that. So it's not it's the deducing this truth is just not that difficult unless you're looking at it upside down.
In the 16th century, Gilbert discovered that the Earth is really a giant magnet, and he experimented with...
No, it's really a giant rock with a tiny, tiny bit of magnet in it. Okay, so that's the way to look at it. It's not a giant magnet. It's a little magnet inside of a gigantic Twinkie or something. You know, it's a little magnet inside of a big blob of non-magnet.
Compasses, and he was effectively the first person to map out the magnetic field of the Earth. And if you take one of those magnetite needles, and the needle is pointing in this direction, which is the direction of northern Canada, then by convention we call this side of the needle north, and we call this side of the needle south.
Right, and it's opposite because obviously the opposites attract. So we're really, the North Pole is really the South Pole, but again, mislabeled conventions that they never fix. You know, so we're stuck with them. We're stuck with the South Pole of the magnet pointing toward the North Pole, or the North Pole of the magnet pointing towards the South Pole in the wrong place. Yeah, we're stuck.
Since A repels A and B repels B, but A and B attract each other, in North Canada is the magnetic South Pole of the Earth, not the magnetic North Pole. That's a detail now, of course. So this is the way that we define the direction, north and south.
It's not really a detail, and you know, I don't even know if they've ever really technically gone to the trouble to figure out which is right, the right answer. Maybe the needle's mislabeled, not the North and South Pole. The North and South Pole are correct. It's the needle that's mislabeled.
Of these magnetite needles. A crucial discovery was made in 1819 by the Danish physicist Ørsted. And he discovered that...
This is something a little bit annoying about Professor Lewin. He's always got to point out when somebody's Danish, every single time. And it's a little bit obnoxious. Like, oh, look what we did for the world. It's just so, it's kind of rude almost. But he always does it.
A magnetic needle responds to a current in a wire. And this linked magnetism with electricity. And this is arguably perhaps the most important experiment ever done.
Yeah, it's just kind of silly. I mean, you know, obviously it would have been an experiment, was inevitable that they were going to find out as soon as they invented electricity, that is, made it go through a wire, that they would have discovered these facts about what happens when electricity goes through wires. So it's kind of such a an obvious round wheel kind of discovery, you know, in the sense that if it wasn't invented on Tuesday, it would have been invented on Friday. It, you know, Ernst didn't save us hundreds of years. You know, he saved us 57 hours, kind of a thing.
Ernst concluded that the current in the wire produces a magnetic field, and that the magnetic needle moves in response to that magnetic field, which is produced by the wire. And
lots of explanations for what the field is, and that's the real conversation. Ethers is what they usually believed in. You know, waves in ether, all kinds of stuff like that. And what it really is rays. Rays of force. Okay? And it just happens to be that you're pushing electron rays at one end and proton rays at the other. You have a disproportion of the, you have a disproportional mix. One end is producing 70% red and 30% black, and one end is 70% black and 30% red. Same amount of force overall, just changed in which way the the specifically oriented force is going.
This magnificent discovery caused an explosion of activity.
So again, it's magnificent discovery. I mean, it's just, you know, this inevitable discovery, you know, based on the discovery of electricity. So again, you could go back to Benjamin Franklin and say, you know, his conversion of this, what do they call it, this heat, this fire, into something that would travel down a kite string, may be more important.
In the 19th century, notably by Ampere, by Faraday, and by Henry, and it culminated into the brilliant work of the Scottish theoretician Maxwell. Maxwell composed a unified field theory which connects electricity with magnetism, and that is at the heart of the...
So Maxwell just took a bunch of these other people's equations, Ampere and Faraday and all those people, and rewrote them, adding these time and speed variables, so you could get a better grasp on magnitude of these fields, this radiation. Good work mathematically, but I'd say bad work in terms of what was the byproduct of that, which was a perception that was a conversion of this ray force into a wave force, and then the application of this idea that these fields must be applied to something called a photon. And now a photon must be electromagnetic, even though photons display no preference for electric or magnetic fields. They seem quite disinterested in those fields, yet it's called the electromagnetic spectrum. It's obviously photons are force. They're not affected by force. They are the force. They're a form of force. They're the bits that affect electrons and protons. They're not the bits affected by the force. They are the force.
This course, Maxwell's equations. You will see them all four by the end of this course. If I have a current, a wire, let's say the wire is perpendicular to the blackboard, and the current goes into the blackboard, I put a cross in there. If the current comes out of the blackboard, I put a dot there. And there is a historical reason for that. You've always talked about vectors in 1801 and in other courses, but you've never seen a vector. And I'm going to show you a vector. This is a vector. And this is when it comes to you. That's when you see a dot. And this is when it goes away from you. That's when you see a cross.
So it's a nice, this was 2002. I mean, physics has made a mess out of vectors now, because now they call all kinds of abstract things vectors, in the convoluted relativity math and the rest of it. They're called vectors, and they really don't have anything to do with things moving in straight lines.
So this current, when it's going into the blackboard, I can put these magnetite needles.
Let's understand, the current is a force going through the wire. Now when the force is going through the wire, the atoms change their structure, form, shape. And they are going to now be in a different arrangement because they're pressurized by this force that's moving like an arrow through the wire. So the force is pushing. The atoms are getting hit by that force and reacting. And essentially this is all happening on the surface of the wire. The surface is where these electrons can move as through the atoms as ions. Going through the center of the conductor, the atoms are all tightly bound. They can't expand, they can't contract. They're kind of rigidly held because they're tied to all the other atoms. But the surface atoms are the ones that have one side that's attached and one side that's not. And that side that's not can do all kinds of things with the outside world. It can expand and contract quite easily. And so that's what's happening essentially, is the electricity is expanding the exterior wires, atoms, creating ions. And those ions mean that for every positive ion there's usually a negative ion. And so essentially I could argue that what's happening in the wire, so if this was the wire, the magnets are lining up like this, or like this. So they're going around the circumference as little magnets pointed this way. Okay. And the consequence of that is kind of subtle. Maybe I'll draw it. And this is just this is the draft part. I mean, this isn't some kind of complete theory. It's just my attempt to explain why there's a variance, a difference. Light doesn't look quite right, but we'll see if it's acceptable or not. We'll find out. I have to move this up, I believe. There. Okay. So as I was saying, the wire is like this. Now the atoms in the center are bound. It's a metal. So the ones on the outside are the ones that can create ions. And let's just say that the ions are going to be repulsive. So as these outside atoms pressurize, they're going to repel each other. So I'm just using this version. So this would be a negatively charged, right? No, positively charged, because it's got protons on the outside. And let's, for the sake of argument, the negative version of these ions would be here, to create a binding. The atoms still have to connect to each other, and there's consequences to when you create one charge, you attract the opposite. So you'll end up creating any negative ions in here are going to migrate towards that positive ion surface. But anyway, so you end up with something sort of like, you have your negative ion. I don't know why I do this with the caps. Like it's going to dry out in 10 seconds. So you end up with these positive ones on the surface and then this one back. Now you could sort of see that if you had two of those. What the hell's going on? Oh man, I'm way off. Sorry about that. Alright, so here's the ions, positive, here's the negative ring underneath, and that essentially is creating this kind of triangle thing. The negative ion is in the back, it's not very accessible, it doesn't have much influence. The positive ions are dominant, they're on the outside, so we would call this positively charged, because the positive ions are going to be much more effective. But the point would be is, See, this is my version of explaining why you have attraction between two wires carrying current the same way. So this is wires of plus, right? That's into the board. And let's say we create another one that's plus into the board. And so these two wires are both, this is a wire. And then this will be a wire. Okay, I know I'm mixing the colors, but you'll just have to learn how to live with that. Now obviously the positives are going to repel, so the positive charges would look like this on this other wire, right? They would tend to go, well, the wire's this way obviously, so they're going to go this way. So they're going to try to keep as much distance between the positives. They're going to be repelling, but the negative to the positive is going to be attracting. So what basically happens with the two wires, so here's, I'll draw them this way. So you have two wires, and the current's going the same way through both of them, poorly drawn again, and they end up attracting, which seems wrong. They shouldn't be attracting. They have the same polarity. So you're saying, no, they should be repelling. But what they're doing is one rotates just a tiny bit, one rotates a tiny bit the other way, to end up matching this scenario where you have this positive ion and this negative one are attracting, and then another positive ion, negative ion attracting, positive ion, negative attracting. And that's why they have to, it's such a weak attraction, you know, because there is this repulsion built into it because they're both positive. The only way it really works is they're negative and positive just weakly when you just turn them the right way. They're generally repulsive, but if they can turn, they'll go positive to positive. So if they have it's just like magnets flipping over. The magnets will flip. They won't stay the wrong way and just pretend, oh yeah, I'll just stay the wrong way and fight against the stream. No, they flip and then go, you know, attract. So they're repulsive, they just flip, now they're attractive. So the wire's just turning to match a attractive force. So again, but they have to put very high currents into it, because it's only with a very high current that this very subtle attraction that exists within this just turn the right way. So 90% of the turns won't work. It's only that 10% in the right turn that works. So it's very subtle. And there's probably experiments that can prove that. You know, where you just slowly turn the wire and it doesn't attract anymore. But I've never seen that attempted. So we will have to wait to see if we can prove or disprove this theory of why two opposites, I mean two things that are the same, attract, because they really shouldn't. But it is a very weak attraction. That's the thing to point out. Very weak. Very high currents needed to manifest the phenomenon.
In this vicinity, and they will then do this. And when I put it here, it will go like this. And it
so in a sense, sort of a recognition of sort of what I'm pointing out. It's positively charged, but the negative charge is there. So the needle's lining up with the fact that the magnet is red, black, red, black, red, black, red. The conductor is red, black, red, black, red, black. And the further away you go, the more you'll see the red, black, red, black.
follow the circle, and this is the way that we define magnetic field and the direction of the magnetic field, namely that the magnetic field, for which we always write the symbol B, magnetic field.
Right, and it doesn't have any, it doesn't move. So every time they draw one of these things and put an arrow on it, there's no vector to the field going around. It's a radial force. It's radiating like a light bulb. There's no swirling. There's no orbiting. There's none of that. And they keep implying it with this evil little arrow, when The arrow should be pointing up, or there should be a asterisk, going in all directions. The magnetic field is not a thing outside of the magnet going around. The magnetic field is a bunch of rays going out from the magnet.
Is now in the clockwise direction.
See,
by convention.
See, it's just wrong. It's not the truth. You need some of this convention just to recognize the difference between north and south. So this is just a concession to the fact that the north end is the electron end, the south end is the proton end. Clearly that's different. So you have to recognize when you're pushing pressure, that is, you have more electron pressure, and when you have less electron pressure. So this is a way of acknowledging that difference, but it's just wrong to imply that there's any such thing as a current outside of the magnet.
Current goes into the blackboard. And if you ever forget that, use what we call the right-hand corkscrew rule. If you take a corkscrew and you turn it clockwise, the corkscrew goes in the board. That connects the B with the current. If you take a corkscrew and you rotate it counterclockwise, then the corkscrew will come to you, comes out of the cork. And that's how you find the magnetic field going around current wires.
Out counterclockwise, in clockwise. Screw in, something out.
It's just a convention. I want to show you how a magnetic needle responds to a current. I have here a wire.
You could just go clockwise, you're dead. Okay, and no, clockwise, well, by the way he said it there, the way it's drawn, he went around clockwise, is the tail of the arrow. So clockwise, you're the perpetrator. Okay, counterclockwise, you're dead. The arrow is going to hit you. It's coming right for you.
Which I'm going to run a fabulous amount of current, something like 300 amperes.
So this is sort of what I'm getting to. This is that to display this effect, you have to put an awful lot of electricity through these wires.
And you're going to see that wire there.
Because the amount of charge that's actually being created on the wire is not much. If you want to get electricity out of a wire, you need lots of wire to create lots of little magnets that create lots of, and then trap it, inside a coil. Then it reflects back and forth, and you gain all of that extra field energy from the fact that the field is constantly trapped inside. It doesn't get out to the universe. It doesn't get away. So it keeps hitting you. You spit, and the spit bounces back in your face, right? And then it bounces off you, and then it bounces into your face again. Then it bounces off you, and it bounces into your face. And every time you spit, the same thing keeps happening. And after 10 spits, you're getting hit, with an awful lot of spit.
I'm going to get my lights right. You see how I want it to go. This is the way I want it to go. Get you optimum light there. When I draw a current, here you see the magnetite, we call it a compass nowadays, and it's lined up in the direction of the magnetic fields of the Earth. We're going...
Well, he calls it iron oxide. It's the same as magnetite, so it obviously is an oxide in some other form than the form we see it in commonly, because common iron oxide doesn't seem very magnetic.
To run 300 amperes through here, and it will change the direction. It will change the direction, which is, there's going to be a magnetic field around the wire like this. So
again, he just drew it. The magnetic field around the wire like this. No, it's going to be going like this, radiating from the wire. It is not cycling. It's just wrong. Sorry, it's wrong. Wrong. It's wrong, 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 wrong.
It will go like this. The current that I run is so high that things begin to smell and smoke within seconds. The battery is not going to like it when I draw such a high current. I can therefore do it only for a few seconds. So this compass will swing in this direction and it starts to oscillate, I can't keep the current so long that it stops the oscillation. So I will stop it by hand and convince you that that's really the equilibrium position. So if you
just pointing out again, they have to really have to force this to be an effect that you can notice. They really have to push it, and that the only way you really gain the effect of this magnetic effect of current going through wires is when you start making the wires fold on themselves and trap the energy between them. That's when you really get somewhere. That's when you're magnifying the magnetism. But on its own, the electricity creates very little magnetism.
ready for that? So we get now connection. Watch it. 3, 2, 1, 0. There it goes. And I'll stop it. The current is still going. That is the equilibrium position. And I will stop the current.
So the equilibrium position looked like it was radial out. So I guess the compass is below the wire. Yes, it must be below it. It looks like it's to the side, so we don't have a very good angle here to see exactly the arrangement.
Now I will reverse the current.
All right, so it looks like it's pretty much right below the wire. So it's going to line up perpendicular to the wire.
Opposite direction. Now you will see that it swings backwards. 180 degrees in a different direction. 3, 2, 1, 0. There it goes. I will stop it. 2 seconds, that's the equilibrium position, and I'll let it go. So you've seen that.
All right, so the point is that the field's coming out in little wedges of red and black in disproportion. More red than black, but clearly when the black's there, it's there, and the needle has to react to it, and especially a big needle. So the big needle is going to feel average the effect much better than a little needle would. A little needle at a distance might be able to move from the different pressure and lose some of its rigidity and its orientation. It might start swinging some more, might go back to original magnetic earth magnetism because there wouldn't be enough of a difference. Another good test would be small needles. A way of doing the experiment, varying the experiment to see if you can tease other facts out of the experiment. They just don't do enough. These experiments are so simple, yet they really need to have this teased out of them. Just like the 2-slit experiment and the single slit, they haven't done any effort to tease anything out of them. They've just sort of made up stories about how, well, if I put detectors on them. They never put detectors on them. They just make up stories about possible variations that they do in their head and say that can't work when they never did it. Mostly because they can't do it, but I'm just saying they didn't do it. They even, it's I think it's really bad science in a lot of ways. It's pretty poor. They don't bother doing experiments. They think about them, but they don't bother doing them.
Indeed, the magnetic needle responded to the magnetic field that was produced by the wire. This was the great discovery by Ørsted. The discovery, this demonstration all by itself, may not be very spectacular for you, but historically it is of enormous importance. I would argue perhaps the most important demonstration, the most important.
Again, just so this would have been such an obvious occurrence, and I don't even know if Benjamin Franklin didn't even know this fact and maybe just didn't think it was all that interesting. I'm not sure. I'm just saying this, to go this far as if this made physics happen. No, this was inevitable as a discovery, especially in small wires without big currents. But you don't need to do this big current thing. You can create the phenomenon really easy by just coiling up some wire.
Research ever done in physics, because it connects electricity with magnetism. It was the foundation of the creation of the whole concept of a field theory. Action equals minus
fields theory. So let's understand, they don't have a field theory, they have fields theories. Lots of fields. Gravity field, bent space, magnetic field, electrical field, and now they have one for every single new particle they create. They create a new field for it. Nonsense.
Reaction, and that means that if a wire that runs a current has a force on the magnet, then of course the magnet must also exert a force on the wire. And I'm going to demonstrate that to you too. But now I have a much more potent magnet, for which I will use this one. And the magnet will not move, it's so heavy that it can't move. So now you will only see the wire move.
So again, using a very strong magnetic field, because the magnetism created in the wire is very weak. So he's just going to basically demonstrate that if I do an opposite polar magnet next to that wire, that the wire will have to move because it's in the presence of another magnet.
And the basic idea is then as follows. Here is that magnet. This is the north pole of the magnet, and this is the south pole. I don't remember which is which, to be frank with you. So the magnetic field would run then like so. And I have here...
So again, he's got it going through the magnet, again, going in a direction, all that kind of stuff, and none of that's happening. You'll never find a magnet moving anything in any tangential direction around it. Magnets merely create a radial field. The radial field has differences in it, and those differences will be detected by other magnets. That's it. There is nothing is moving around the magnet. Nothing.
Current wire, a wire that runs a current through it. The wire is perpendicular to the blackboard. If, when I turn the current on, if current is coming out of the blackboard, then I have 50% chance because
then your magnet is backwards, right?
I really don't remember whether this is north or south. But let's assume that this is the configuration, that the current is coming out of the blackboard. Then you will see this wire experience a force up. It is an experimental fact that the force on the wire is always in the direction of I cross B. These are unit vectors. And since I is coming out of the blackboard, if I cross I with B, I get a force in this direction. And so if I reverse now the current, if the current goes like this, then of course the wire wants to go down. And I will show you both. But I don't know which.
So it's kind of just deciding whether the wire turns left or turns right, sort of getting towards, motors. Let's see if there's any way I can interpret this to explain it, why it matters. Well, I'll have to have an add-on for the why it matters, because I don't know why it matters at this particular moment. So the wire is producing a magnetic field, and there's a reason why it's going to obey some kind of spin rule. That is, it spins up or it spins down. And that's essentially what's being argued. So I guess the argument is it's going to turn one way, pushes, and then once it turns, that rotation keeps tending to push it down one direction. And turning up will do the same thing and push it up in one direction. So that's sort of the argument, is which way will it turn based on north and south. So it's sort of saying that if I have that two protons and then I have this electron down here, the argument is that if I reverse that configuration, not reverse it, if the other side is doing exactly the opposite, then the point would be the two will, because one's sorry way to say it, one's getting hit by the north side, so this is pulling, and one's getting hit by the south side on the other side. So you have these two arrangements on either side of the conductor, more like this way in this example. And the north side is going to pull one this way, and the south side pushes down this way, which has to do with hitting the protons versus hitting the electron, the negative ion. So one's going to be pushing on the negative ion, the other one's going to be pushing on the protons, and that's going to decide whether it goes down or whether it goes up. Which one you're pushing on, because the positive ions are on the surface, the negative ions are inside. If he reverses the polarity, then the negative ions are on the outside and the positive ions on the inside. And so it just changes which one you're pushing against. So one side is pushing harder than the other side down, and then when it's the other way around, it pushes more this way than that way. Yeah, that makes sense. Mostly.
Which one will come first? Because I didn't mark the poles. Oh, so you'll see it now.
Seems over time they would have marked them, but maybe it doesn't matter whether you mark them because you could plug it in either way.
Slightly different from the way I have drawn it. I've drawn you the magnet looking this way, but it's of course much nicer for you to see it this way. So you see the wire, and there is the magnet. And now I'm going to run a few hundred amperes through that wire, and then it either will jump up or it will jump down, and then I will reverse the current, and then the opposite thing will happen. Okay, we ready for this? 3, 2, 1, 0.
So the thing that would be interesting is to see whether there is any torque on the wire, whether the wire actually turns, like trying to turn like a magnet would turn. It's trying to turn, but it can't turn because it's it's twisted and it's tight. So it's trying to turn, but it can't. So it's a torque pushing it down. It wants to turn, can't turn, so it gets pushed down instead.
Notice there was a distinct force down. The force was so high that it even pulled down the supports. So now I can predict that if I reverse the current from this experiment, that now the wire will jump up. There we go. I know now exactly because I switched it this way, so now I will switch it this way, and the wire will jump up. That's the first drawing you see. 3, 2, 1, 0. Very clear. You saw it come out. Okay. Let me take this down. All right. If I have a wire through which I run a current, let's say I run a current I1 with this wire, it will produce a magnetic field, right-hand corkscrew, right here. That magnetic field will be in the blackboard. I'll call it B1. Right here, it will be out of the blackboard. But that's irrelevant right now. But it's out of the blackboard. Here it's in the blackboard.
Now that didn't make any sense. So he's saying, okay, so he's doing this turning around thing again. So the magnetic field is going around, okay, which it's not doing. Anyway, it's just so wrong. So he just didn't draw the going ins on the other side. So he's basically putting a coil around. Again, he's just thinking about going around the wire. So the wire's going this way. He's thinking in terms of the field going around, which it's not doing.
And here, I have another wire. I'm going to run a current I2. There will be a force now on this wire in the direction I cross B. Take your hand, I cross B, that force is up. So this wire will experience a force up. But of course, if this wire experiences...
So he's just, this is the two conductors going the same way thing that I pointed out before. I think that's where he's heading here.
A force up, since action equals minus reaction, this wire will experience a force down. So they will go towards each other. They will be attracted by each other.
Let's understand, they're never attracted. They're just less pressure in between them. It's always an external, everything that moves together because some external force is pushing. And it's only because you've created low pressure that you ever have something called attraction. So there's no attraction without lowering pressure. So, and lowering pressure means that your arrangement, you've arranged the red and the black in such a way where the red is pointing towards the black. Therefore, the red energy is escaping the black energy is escaping through the red. So the only time you can have attraction is you have to have some alignment between that proton and electron that somehow that does dissipate the pressure between them. So now they're not reflecting. If they're the same color, then the reflections are happening back and forth, the spit. It's perpetually, and it just keeps getting more and more and more energetic. If you radiate anything, the radiation keeps, it's stuck. And so any distance change just creates more pressure. So you're just pressurized. So there's too much, so the point is if those two wires are attracting, that means that something has to be aligning up where it's red to black. And so as I pointed out, what's happening is the positive ion positive, so just pretend this is red, and the negative ion's back here. And so if you align the two up right, this negative ion will line up with a positive ion on this side. And that's what's causing the wires to...
You can in an independent way confirm that the force here is down. So this is the force. For me, it would be enough to say action equals minus reaction, Newton's third law. But if you want to put in here...
Yeah, no, sorry, this has nothing to do with that, in my opinion. Yeah, really nothing. If I just turn those wires, I'm going to have the exact opposite effect. The wires are going to be pushing apart. This isn't, obviously, that's not action equals reaction. When the two wires are flying apart, you're not going to call it action equals reaction. So you can't really do it when they're moving towards each other either. The principle is just wrong. It's just wrong to say action equals reaction when the two wires are moving apart. You wouldn't say that, because it's going to look like one action.
The magnetic field B2, which is the result of this current, which is of course out of the blackboard, remember the right-hand corkscrew rule, then you will see that this force now here must be in the direction of I1 cross with B2, and that's down, which is exactly what I predicted. So the two wires will go towards each other. However, if I leave everything the same, but I reverse the direction of I2, so now the two currents are in opposite direction, then the forces will flip over, and so now the two wires repel each other. And I will demonstrate that to you.
That's sort of obvious, right? So we're just, again, just pointing out. We already pointed it out, so we won't bother continuing to point it out. If you have the current going the opposite, then the positive ions are the stronger force, the exterior force, is different on both wires. Yeah, it's different on both wires. Alright, well, anyway, that'll take a little more work. Yeah. But just I'll do the opposite of what I said before, and somehow that's going to work out. Trust me. Trust me. Just has to do with the alignment. So when they have opposite polarity, they're going to have, the outside is going to be, one of them's going to have the positive ions on the outside, one's going to have negative ions on the outside. And they're going to have the opposite thing on the inside. And the problem's going to be they won't be able to find that alignment. You know, there won't be an alignment that's low pressure. Well, they really should. All right. This is sort of important, these details, so I will, in the next episode, attempt to fix what I'm sort of running into is a cognitive problem with matching the two circumstances to the same principle. So I'll work on that.
I have those two wires here, and you will see them there on the screen. I will explain what you're looking at in some detail. The two wires run vertically. This is one wire, and this is the other wire. And when I run the current in the same direction, then they will attract each other. And you will see that shortly. 3, 2, 1, 0. See, they go towards each other.
So, like I said, that's just sort of opposite of what we would, the intuition. Your intuition is, well, they're the same polarity and same polarities, you know, red, black, same magnets should repel. And they're not repelling, obviously.
I'll do it again. No. If I run the currents in opposite directions, they will repel each other. Now I run them in opposite direction. They repel each other. I'll do it again. 3, 2, 1, 0. They repel each other.
Quite obviously. I I don't know if they do it across the length of the wire. That's another. So, I mean, again, it's a little bit tricky. I mean, how flexible the wire is. It doesn't seem to repel at the top and the bottom as much as it does in the middle. But that might be a tension argument or gravity argument or some other kind of argument about the weight of the wire at different locations. Again, so now they're going in opposite directions, the current, which should make them attract, and yet they're repelling. Okay. Interesting. Yeah, sorry. There's a reason. You know, I know there's a reason. It just has to do with the positive and the negative ions. So an obvious truth would be is the negative ions are big, let's say, and I mean the positive ions, the ones that see, negative are the ones that have higher pressure, right? So the high pressure ions are big, the low pressure ones are small. So maybe that's what it has to do with, and the big ion is the one in the back, and so it's the big ion now that's dominant, you know, the pressurized one in the back. So it has two positive ions on the outside and the big negative one. Again, sorry about the sign conventions are just insanely irritating. Yeah, so I have to size the ions to indicate pressure versus low pressure. And so that's why they're repelling, is because it's really just about the orientation of the ones that have the high pressure. So when the currents are going in the same direction, the ions on the surface are probably the low pressure ions, and when you reverse that, then you have one that has low pressure on the outside and one that has high pressure on the outside. Well, it's really about which way they're twisting, though. Okay, sorry, I can't, you know, thinking in the middle of the video is really a bad idea, so I apologize for that. Alright, let's play it and then I'll have to fix it.
The reason why I showed you this demonstration is a different one. Well, I want you to appreciate that if I have this conducting plate of aluminum, it's a conductor, and I put that in between the two wires and I repeat the experiment, that exactly the same thing will happen. And that tells you that magnetic fields are really very different from electric fields.
So it's not true. Because if he stuck that plate between two electric fields or magnetic fields, it doesn't make any difference. If he did it between two charges, the plate's just going to go positive negative. It's just going to repeat the same cycle. So the positive side over here will just create a new positive side over here. Alright, the two end places will have the same voltage, and he'll be able to take a voltage off of here. There'll be half the voltage, but it really won't change anything. It won't change the attraction of the two outside plates at all. So, you know, this is a bad proof of anything. It doesn't prove anything because you can't use that metal plate to disrupt an electric field either. A charge field isn't going to be bothered by that plate. It's just going to charge and duplicate the same scenario. It's not going to change it any.
Because the electric field would be heavily affected by a conducting sheet like this. Magnetic fields are not.
It wouldn't be. What would be is certainly if you're shooting electrons at it or something, then yeah, it's going to be a barrier. But shooting electrons is different than the energy itself. The force will not be affected by that piece of metal. Electrons will.
So what I'm going to do now is I'm going to put this plate in between, and then I'm going to again put the current in opposite directions, and so we will see the wires repel each other as if the plates were not there. 3, 2, 1, 0. There you go. So magnetic fields have a very interesting story to tell.
So again, like I said, if he had two charged plates and he did exactly the same thing would have happened. the pressure of the two charged plates, if they have the same charge, they're going to be repelling, so that part's opposite than the wires. But the fact that there'll be pressure is going to be fact, and you won't change the pressure only by sticking a piece of metal in between the two. You'll just create another pole that you can take electricity off of, but you won't change its 10,000 volts of repulsion. That'll stay exactly the same.
However, electricity and magnetism are connected.
If you stuck an insulator in, then you're going to get a different result. So it just gets complicated.
How do we define the strength of a magnetic field? With electricity, we defined the strength.
The other problem is that sheet he put in there was probably paramagnetic, which also complicates the circumstance. Probably aluminum or steel.
Of electric field in the following way. We measured the force, the electric force, on a charge, on an electric charge, and then the electric force is the charge times the electric field. That determined the strength of the electric field. Wouldn't it be nice if we could now say, okay, the magnetic force is a magnetic charge times a B field.
So again, the problem with this is this electric force thing, because it doesn't say anything. It sort of says voltage, but it's not saying voltage, but it sort of is. It's a pressure argument. The strength of the field is based on its pressure. And again, you could argue that, well, yeah, magnetic fields, you can't regulate the pressure. It's only 1.5 volts, let's say, and it's always 1.5 volts. So you can't regulate the pressure to change the field, where with electricity you can regulate the pressure and change the field. So that's a big difference. But there aren't two, like again, you got an E field and a B field. They're the same field, and all you have is different ways of affecting the field.
But that would then define the magnitude of the B field.
Different purities. So the stuff going through the wire is really pure. That's all black energy, black force. The stuff the charge is radiating, substantially black. Only the black stuff gets reflected from a negative charge. The magnet, lots of mixing, but a huge density. So therefore, even though it's very mixed, there's a lot of it.
It would be nice, but as long as we haven't found a magnetic monopole, we can't do it. If you come with a magnetic monopole tomorrow, I can do this.
Yes, well, you can do it. It's just, yeah, and you didn't even try to do it. But if you did it with magnets, you just have to come up with some kind of way of quantizing the Q. There's no Q, there's no electrical charge to the magnetic monopole, quote unquote, because it's atomic. And you have to know how many atoms there are in the magnet or something. It just doesn't, But I suppose that would be possible, is to somehow calculate the density of the material and how much of the material is magnetized. But that gets a little bit, there's no simple way to do that.
But we have no magnetic monopole, and so it cannot be done this way. How is magnetic field then defined? Well, it is defined in the following way. I take an electric charge, and the electric charge is Q. And if that electric charge moves with a velocity v, and there is a magnetic field where the electric charge is moving, then it is an experimental fact that the force is always perpendicular to v. If you want to call that B with a magnetic indication, that's fine. So there's a magnetic field, the charge is moving with this velocity, and there's a force on that charge which is always perpendicular to v.
So again, I would argue there's a force on it is the wrong thing to say. The field force is going to be affecting the charge because the charge is a magnetic monopole, so it's going to affect the magnetic monopole. So you didn't put the B field in here, so he's just got a charge moving. He doesn't have the field that's supposed to be putting a force on it.
The magnitude of that force is proportional to the speed of the particle, and it is also proportional to the charge itself. If I double the charge, then the force doubles. If I double the speed, then the force doubles. And so the way that we define now magnetic field strength is this way. The force, and I gave it a B to remind you, magnetic is Q is the electric charge, U is the velocity of the electric charge, the cross product with B. And you see that the force...
So he's saying B, and he's got B in the same thing, and one's the cross product of a vector, so it's a little bit hard to figure out what these B's would be. Obviously, having them on both sides of the equation just makes it a little bit confusing, I think, but whatever.
Is always perpendicular to V, and that it is linearly proportional with the speed and linearly proportional with the charge Q. And this is often called the Lorentz force, after the Dutch physicist. This equation is completely sign sensitive. If you change from a positive charge to a negative charge, then the force flips over 180 degrees. You change the direction of V, force flips over. Change the direction of B, force flips over. So it's a completely sign sensitive equation. The unit for magnetic field strength follows from this equation. This is newtons, Q is coulomb, and V is meters per second. So this would be the unit for magnetic field strength, but no one would ever say that. In SI units, this would be SI units, we call that 1 Tesla, for which we write 1 capital T. The Tesla is an extremely strong magnetic field.
Yeah, because a Newton is gigantic also, so that's the problem with that one. So, yeah, I guess we'll go a bit further.
The magnetic field of this magnet is only 2/10 of the Tesla, and that's a very strong magnet. We often use, therefore, a unit which is the Gauss, which is not an SI unit, but you'll see it often in books, and 1 Gauss is 10 to the minus 4 Tesla. The Earth's magnetic field is roughly half a Gauss. And so this magnet is about 2 kilogauss. But the SI unit is Tesla. If you had looked at the television...
I suppose he means the magnetic field on the surface of the Earth.
In 2002, when I gave these lectures, on the screen of your computer, you have a fluorescent screen, and in television there are electron guns that raster scan this fluorescent screen. On the television screen you have 525 lines, and the electron guns scan that in 1/30 of a second. And the intensity changes of these electron beams create images. So if you look at the two...
Alright, so sort of, this gets into some more theory about what's really happening between these electrons, how they're being shot. And there's really just a force. So you're shooting force. And the only way the force can be conveyed is, again, these arguments, it has to be conveyed through matter bits. So there's electrons that you're pushing, but you're really pushing a stream of electrons. So the electrons are in a stream, and you can understand the force is still reflecting back and forth between each one of the electrons in the stream. They're still pressurized, and you're just pushing the back one. Okay. And that pressure moves through all of them, and so it just keeps accelerating the tip one. Yeah. It's a train of electrons, and the propulsion is in the compression.
From the side, then there are electrons. One moment in time they may move like this, another moment they may be here in the raster scan. And so it's clear that if you bring a strong magnet...
So when you bend them, no, the force is still going in straight lines. Force isn't bending. But the electrons, you can pull them off the force in different locations, different ways. But the force is still going through. The anode and the cathode. The cathode is huge. The anode small. Right, anode producing, cathode receiving. I always get it backwards, but anyway. So you're just making a big negative pole and shooting your positive here. So you have lots of force going across, and it really doesn't matter where you put the electron. It's going to get pushed by that force. But it's force that's going from point A to point B.
In the vicinity of your television screen.
Photons. Photons are pushing. We see the electrons, but the photons are what pushed it. The invisible photons.
That you will distort the image, because you are now affecting the motion of these currents, of these electrons. And there is a very famous artist, Namjoon Paik, who used this for his art, and almost every major museum in this world has a work by Namjoon Paik.
Bet on them, I would say.
With distorted images using magnets and using television screens. I don't want to compete with Namjoon Paik, but I do want to show this to you. I have their television set, and I have a very strong magnet, and I will try to distort that image and give you the best light that we know how to. And I suggest we try to find a program that we hate. So here is my magnet. Oh man, this is an extremely strong magnet. And let's turn on the television and let's see what we can get first.
I didn't turn it on, I don't think.
Oh, I turned it off instead of on. Working time.
The Fox owners are talking about manager Joe. I don't think.
Neither do I. I hate commercials. Let's go for a commercial. I hate commercials. Now watch it closely. Here comes my magnet. There's the image. You see that? Don't do this to your own computer, because what
you'll see is nothing swirling, nothing moving anywhere, no speeding up and swirling and vortexes and whatever, nothing looking like it's going somewhere.
If you have done this, it may never look the same.
Just landing
but these
in different
electrons
places.
now. Can you see it? Can you see the distortion? Can you see the distortion? You're so quiet. Okay. So you've seen.
Okay. Probably a good enough place to stop. I just had a thought on what I was talking about the wires and the reflections. I don't know if it's worth doing now. So yes, I'll wait till next time. See, it's just when you create this positive ions on the outside, negative ion in here, there's two ways you could see it. The magnet's going this way, or the magnet's going this way, because they're going to be sharing a negative ion, essentially. But not really, because this one's sharing this one over here, too. So you could see the magnet going this way, or you could see the magnet going this way. So it's like it's not a dipole, it's a tripole, and that it has one positive pole and potentially two negative poles, either one of these. Yeah. Yeah. Anyway, so yeah, so that might work. I have to think about it. So anyway, till next time. Sorry about the little confusing this and that bits, but I'm sure it has something to do with the arrangement of the ions, and that's why you have this opposite effect of something that has symmetry, same direction, attracting, when we know that everywhere else it's the opposites attract, not the sames. So there's a reason why there's this exception, and it should be explained. Needs explanation. Clearly they don't explain it. You know, so I'm going to attempt to give you the mechanical explanation. Alright, so that's enough, I think. So, till the next time, and such. Hopefully recorded successfully.